All right, so today we're going to be talking about acceleration. And acceleration tells us about the rate change of velocity, kind of like velocity told us about the rate change of position for something. Us, you, a ball, a cat, a dog, a car, a spaceship, whatever, okay? And the equation that you see here on the left is for average acceleration. And that looks a lot like our equation for average velocity, but of course with some important differences. Okay, primary among them is that we have here in the numerator a delta v, so a v final versus minus a v initial. So that tells us how much the velocity is changing, and then we divide that by delta t, the period of time during which that change of velocity happened, and that'll give us the average acceleration. Okay. Now, let's take a quick look at units here, because generally speaking, you can look at displacement and position and be like, okay, that's units of meters if you're using the fundamental unit, because it's a length or a distance from some, well, distance is a fraught word, okay, but in terms of its definition, but a length, okay. And velocity, we're used to measuring things in miles per hour and kilometers a second and all of this kind of other kind of things. So we're used to units of velocity, the standard one being meters per second. But perhaps we're a little less used to thinking about the units for acceleration if we haven't had physics before. And so if we look at the quantities in the numerator and denominator here, well, all the things in the numerator are measured in meters per second, and all the things in the denominator are measured in seconds. So acceleration has units of meters per second, which is a little bit of a mouthful, though gets the point across. So usually that's reduced to meters per second squared, okay? Not meters squared over seconds squared, but meters over seconds squared if you do a little bit of algebra on the units there. And that's what we'll be using predominantly in this class to describe accelerations, all right? Now, it's the rate change of velocity. Let's look at an example of what that means for a simpler case, the non-general case. And a simpler case would be to look at a constant acceleration. If you have a constant, and in this case, positive acceleration, because I'm above the axis as I've drawn it, well, that means, in terms of our graph here, where we've got acceleration in meters per second squared on the y-axis and seconds in time, or sorry, time in seconds on the x-axis. Well, if we say it's constant, then whatever value it is, we don't specify here, but say 4 meters per second squared, well, then that's going to be the same for the entire period of time that we consider it. All right? That makes things considerably simpler in terms of how we can predict what the velocity of the object is going to do over time, and also what the position of the object is going to do over time. Just like with velocity, acceleration is going to be the slope of a v versus t graph. There's a couple of different ways to see that. The most basic is just to take the definition of average acceleration that we've got over here, multiply both sides by delta t, and end up with something that looks like this, okay? Where delta v is on our, those v's are on our y-axis for a v versus t graph, and the delta t's would be on our x-axis for a v versus t graph. And so the average acceleration, and in general just the acceleration, is the slope, okay, at any particular time. So let's take a look at that. So I've selected a situation where the initial velocity of this object that's accelerating is 0. You can imagine shifting this line up or down depending on what the initial velocity was, whether it was negative and then you have a positive acceleration, so you get less and less and less negative. You briefly cost 0 and then go up positive. I can draw that in just so you have an idea of what that would look like. So the slope would be the same. I think I've done a pretty good job, not a terrible job drawing that, okay? but the initial velocity would be offset. And the same thing if you were to shift it up. If you were already moving at time 0 at some number of meters per second, then you'd preserve the slope, but you would be shifted up on the axis there, okay? But the important thing to realize is that because this acceleration up here is constant, then the slope of our v versus t graph is going to also be constant. And what has a constant slope? Well, a line, okay? And that, in this case, is going to be a positive slope because we have a positive acceleration here, right? It's above the axis. But we could just as easily have a negative constant acceleration, have a negative slope for our velocity versus time graph. Technically, zero acceleration is also a constant, but wouldn't be a very interesting one. In that case, the velocity graph would have a slope of 0 for all time that we're considering. All right, now that's pretty simple, very analogous to looking at velocity on an x versus t graph and equating that to the slope of an x versus t graph. But let's look at the x versus t graph for something like this, where we have a positive constant acceleration. If we have a positive constant acceleration, then we have a linear v versus t graph. In other words, we are increasing for every second that goes by the same amount of meters per second. Hence that meters per second unit on acceleration if you're not into the whole brevity thing. And then when you go to x versus t, you have to think about it maybe just a little bit more, but not too much more. If we start at 0 velocity here, well then the slope for an instant on our x versus t graph down here is also 0. And if we move along in time so that we're just a moment later where the velocity is relatively small, then the slope of this graph down here at that moment is quite small, close to horizontal, but not horizontal. And then if we play the tape forward a little bit and think about the velocity out here, well, the velocity is significantly larger. And so when we look at the slope of this x versus t graph at that point, which should be indicative of the velocity at that point, well, that's a significantly larger slope than what we had down over here, right? So, and that slope increases linearly, right? Because velocity is increasing linearly, so the slope of the x versus t graph also increases linearly. What you get in that case is an x versus t graph that is parabolic. So if you have a constant acceleration, whether you're talking about a negative acceleration, constant acceleration, or a positive constant acceleration, you're always going to end up with a parabolic x versus t graph. And when we get around to our equations of motion, we will see that for constant acceleration, we have this t squared dependence of the position of the object on the time, okay? Assuming a constant acceleration. All right, so as far as, looking at accelerations in general, remember that for any curve, right, if you want the instantaneous acceleration, the acceleration at a particular moment in time is going to be equal to the time derivative of the v versus t curve, right? We'll do these derivatives on relatively simple functions for the most part in this class, but again, the geometric interpretation of the derivative as a slope is the most important concept you can take away from that equation, I believe. Now, of course, accelerations aren't always constant, right? I mean, you can imagine like, oh, I'm going to gently accelerate away from this stop sign, and then I see a truck coming towards me. I have to accelerate out of the way, so I'm going to jam on my gas pedal and zip out of the way. So I've gone from a low acceleration to a very high acceleration, all in a short period of time. So this acceleration versus time graph can look very different than this. It might, be in that situation. So like, oh, okay, we're cruising along here, and then suddenly, really jam on that gas pedal, and then we have a higher acceleration. Well, in that case, the equations of motion for the car or whatever object we're describing become more complicated, right? As we will see. But the basic connection between the acceleration versus time graph and the v versus t graph and the x versus t graph is more or less the same, right? In this case, let's see, let's give myself a different color here, so we don't get confused. If we were to use this red line on our A versus T graph, and we were to draw in a line that's roughly corresponding to it on our V versus T graph, well, remember that the V versus T graph, the slope of that graph is going to be equal to the acceleration at any particular moment. So if we're accelerating slowly, then we could imagine sort of just kind of creeping up linearly here for that period of time. And then it would markedly increase until maybe we get to this point. And then the way I've chosen to draw it, I have another straight line, right, at a much higher slope, corresponding to this portion of the acceleration, and this lower slope line down here, corresponding to this part of the acceleration graph, and then sort of a transition between the two in here, where the acceleration is varying as you jam on the gas pedal, and thus the slope down here is also varying. All right, so just a few things about acceleration. We'll be talking about acceleration a lot in this class. It's connected to so many different things, including forces and Newton's laws and whole lots of other things. Okay, so we'll be coming back to it, but here's the basics, and I look forward to the next video.